If you're here for this Discovery Talks, thank you. If you're not here for Discovery Talks, now you are. So thanks for showing up. I am excited for you to, I should introduce myself. I am Dean Nicquet Blake. I am Dean of the Graduate Division and Vice Provost of Student Academic Affairs here at UCSF. And I have the pleasure each year of hosting this event, which is the signature event for the Graduate Division. We have a solid lineup of speakers today, and so they told me, get done with your introductory remarks quickly because no one wants to hear you. They want to hear the speaker. So here we go. The Discovery Talk session is the Graduate Division's signature event during Alumni Weekend. It gives us the opportunity really to highlight the amazing research that is being conducted here at UCSF. Just for context, because I know that all of you are not alumni of the Graduate Division. The Graduate Division is a home of graduate education and postdoctoral training at UCSF. We offer 20 PhD programs in basic translational, social, and population sciences, 13 master's programs, a couple of certificate programs, and 3 professional degrees. And we also serve more than 1,000 postdoctoral scholars on our campus. Today we will hear from 6 faculty members who are engaged in training of graduate students and postdocs. They have a really tough task. So they're going to talk about their complex scientific work in 6 minutes or less. If you think that is an easy task, just wait till you hear them, but that's why we have rock stars here. Now, last year we ran a little experiment and during the Discovery Talks, and we added a student to the lineup. So we had faculty plus 1 student. And it turns out that experiment went so well, we decided we're going to experiment again this year. So this year, you will also hear not only from a student, but from a postdoc, who, both of whom participated and won our Grad Slam and Postdoc Slam. Now let me tell you what that is. So every year, we want our students to be able to communicate well to a variety of audiences. So we train them, and then we ask them to perform on stage in front of groups like this for 3 minutes. They're talking about their complex work in 3 minutes or less. So the first series of folks you'll hear are the faculty. The last 2 will be 1 student and 1 postdoc. And just be prepared to be amazed. Now, a few logistics. Audience, you have the hardest part in this process because you're going to hear talks and you're going to want to ask questions. And I'm going to tell you you can't. So here's what I would suggest. I would suggest that you just take out your phones, and when you think of a question, write it down. Or, for some of you old school folks that have pen and paper, that works too, right? But any kind of device that you have that can write your questions on, do that. Because at the end of this, we're all going to go downstairs. All the speakers will be downstairs, and you'll have ample time to talk to them. So you have the hardest job. With that, I am going to say, enjoy the ride.
Now, please welcome to the stage Dr. Jarman Ye with Changing the Aperture Using Photo Voice to Reimagine Age-Friendly Cities.
While in grad school, a professor told me something I've never forgotten. We're all pre-dead. Nobody gets out of this alive. What they meant by that was we must think critically about how life chances are structured from our first to final days, from one generation to the next, and what we can do to improve equitable outcomes. As a sociologist and gerontologist, I study how social structures shape human experiences across the life course in our rapidly aging society. My lab investigates social justice issues affecting older adults, people living with dementia, and caregivers who wish to age in place, which is the ability to live in one's own home and community regardless of age, income, or ability level. Today, I'll take you on a journey through San Francisco. officially registered as an age-friendly city with the World Health Organization, which has these 8 domains of urban life that define this designation that you see at the bottom of the slide. When you hear the phrase age-friendly, you might envision wide sidewalks, accessible public transportation, available health care, or engaging senior centers. But here's the thing. Despite San Francisco being rated the best big city to age in place, according to AARP's Livability Index, the lived realities tell a more complicated story. For my research, I didn't just examine policy documents and statistics. I spent over a decade conducting ethnographic fieldwork, interviewing older adults, and giving them disposable cameras to document their environments through a method called photo voice. Let me share 4 stories that reveal something profound about aging and inequality. Andre, 64, lived in a single-room occupancy unit in the Tenderloin, San Francisco's Skid Row. When I asked what an age-friendly community meant to him, he laughed and said, like Leave It to Beaver, it's the complete opposite of here. For Andre, the term age-friendly evoked a middle-class, predominantly white suburb bearing no resemblance to his daily reality. In his neighborhood, he said, the only thing to participate in is drugs. If you got a pipe and a lighter, you're participating. Andre sought part-time work, but sensed he was too old to be hired. If Andre had power to implement any changes, he would clean up the block. He died at home alone in 2020. George, 87, grew up poor with 5 siblings. In older adulthood, he lived on a fixed income and was incredibly resourceful about what he called clean living. This was his way of maintaining control amid increasing precarity and insecurity with growing older. He volunteered weekly at a food bank, which gave him first dibs on new shipments. He had a unique strategy for storing food, religiously separating items into single-serving containers to prepare for a future when he might be physically unable to leave home. George explained, everybody's got to die sometime. Nobody's going to beat that trip. Once you're born, you start dying. It just depends on how long it takes. I'm happy because I've been lucky. You've got to be clean to stay healthy, but you've got to eat good too. Godfrey, 67. Godfrey loved the Cub Scouts as a kid because everybody was together, stayed together, did everything together. After moving to a new city at age 10, he started getting into trouble with the law. After spending decades in prison, Godfrey lived on less than $100 a month after paying rent. Without a stove or a refrigerator, he survived on non-perishable food and canned beans he warmed on a coffee pot. His strategy for aging safely, he said, mind myself, stay in my room, don't bother nobody. When I asked what he did for fun, he said, I stay in my room. It's fun because I can look out the window and be free to be myself right in my own room. This was a profoundly purgatorial description of aging in place. Godfrey had grown from the kid who thought the Cub Scouts was fun because everybody was together to the older adult who found his only freedom was in solitude. Odom, 64. Odom became unhoused after his wife died. He'd raised 5 kids with her who were all grown. I'm aging, he told me, but I don't have that place to age in. I wish I had a place to age with me. As we sat on cardboard on the sidewalk, Odom compared himself to Dorothy from The Wizard of Oz, caught between worlds, wanting to click his heels and find home. To retain hope, he said, I guess you could say the courage of the lion, like in The Wizard of Oz. I'm gonna need that because it's the only way out. These older adults had modest desires to survive with dignity and with their mind, body, and soul intact. Their survival tactics were acts of creative resistance within a system designed to marginalize, exclude, and expel them. While all older adults engage with the same age-friendly policies at the macro level, their micro-level realities are shaped by identity and socioeconomic inequities that don't simply disappear with age. As Dr. Bob Butler, founder of the National Institute of Aging, once said, when we talk about old age in America, we're talking about our own future. Yet old age in America is often a tragedy. But it doesn't have to be tragic. To create truly inclusive environments, we must recognize that aging intersects with other aspects of identity, address the social drivers of health, and listen to the stories of people like the ones shared today. Insights often come from unexpected sources, if only we change the aperture to see new configurations through different lenses. I challenge you, when you return to your communities, ask not just, is this age-friendly, but who's being left out of our vision of age-friendliness, and how can we create communities friendly to all who age within them? Let's reimagine aging not as a tragedy, but as a triumph of collective care, multiracial and intergenerational solidarity, and social justice. Thank you so much.
Please welcome to the stage Dr. Anita Ho, whose presentation is on Live Like Everyone Knows When You May Die.
How's everybody doing? I'm curious, if AI can predict life expectancy, who wants to know how long you have to live? Okay, so for the few of you who do, what would you do with that information? Would you want your family, doctors, or health insurance companies to have that information? My research focuses on ethical AI in healthcare. In my book, Live Like Nobody Is Watching, Relational Autonomy in the Age of AI Health Monitoring, I use different use cases to explore how being continuously monitored and analyzed by AI may give us better health predictions, but may also compromise patient autonomy or care relationships, especially if we don't have ethical guardrails. So currently, one AI use case I'm looking at is mortality prediction algorithms, or MPAs. These models are increasingly being developed to predict anything from 48-hour mortality in the ICU to 2-year mortality for people living with various chronic conditions. I'm currently leading a qualitative research project in Vancouver, Canada, to explore clinicians and cancer patients' perspectives on MPAs. Our preliminary data analysis revealed 4 levels of ethical considerations. First, what are our goals of using MPAs? This gets to the who, how, what questions. Different stakeholders may want to use the information for different purposes. Doctors may want the information to determine the benefits and limitations of aggressive interventions. Health systems may want to use the prediction to flag patients for palliative or hospice care to reduce in-hospital mortality and length of stay. Insurance companies may want to use the prediction to determine authorization for different treatment options. Patients who are at the center of it all may want prognostication information, but may worry about what insurance companies may do with their data. So if we want to use mortality prediction algorithms, we need to be really careful about aligning the different stakeholders' perspectives to ensure that we have the right goals. Second, even legitimate goals may hide biases. If we have missing data, or if we don't, or our training data does not really represent the intended populations for our models, we may have inaccurate predictions for certain populations. This, to me, is ethically concerning, especially if the predictions may unfairly affect certain populations' access to beneficial treatments. So if we want to make sure that we're using these right data, we really need to make sure that we are training on models with representative data. We're also validating and also fine-tuning our models for the right goals, and make sure that we are also testing these models with the right scenarios to ensure that we have accurate predictions for all different populations. Otherwise, if we somehow try to transition patients who have low social economic status to comfort care, but continue curative treatment for patients who are equally ill but have better support, because MPAs predict that some patients who have lower advantages may die sooner, we may be exacerbating the disparity. Third, medicine is highly regulated, but health AI models that are not medical devices don't require regulatory approval. Sometimes what that means is that we may have different models that are working well for certain populations, but not others. And we need to make sure that we have the right process, because if they are not regulated, patients and clinicians have to make sure that they have the right kind of governance structures in institutions throughout the MPA life cycles. Our participants wondered, whether patients would be informed about when or how MPAs may affect care decisions, how their data or these predictive data may be used, shared, or for what purpose, and whether there may be auditing mechanisms to ensure the predictions are accurate and that we have effective implementation. For example, if we're using these predictions to nudge goals of care conversation or hospice referral, do we have the right kind of resources for the increasing referral volumes? And do physicians feel ready to have these conversations? Fourth, in the age of AI and big data, our everyday life and illness experiences are increasingly being quantified, shared, and used for different purposes, sometimes without our consent or even knowledge. We now have vast volumes of not only clinical research and genomic data, we also have a lot of consumer data from virtual assistants, wearable devices, or health apps. Certainly, multimodal data can help us to have more personalized predictions, but mortality predictions are still imperfect. So what kind of evaluation and appeal mechanisms are there if patients or clinicians disagree with the predictions or worry about how these predictions are used for care decisions? MPAs get to some of the most existentially sensitive issues about life and death. So how do we make sure that we have the right response mechanisms to deal with ethical and clinical uncertainties? After all, automated predictions can still lead to self-fulfilling prophecies. If we stop treatment for patients who are critically ill and have low social support because models tell us that they will die soon and that the patient does actually die, we may think that the MPA is accurate. But we wouldn't know what would have happened if we had continued curative treatment or at least have given the patient more social support. MPAs are going to be increasingly available in healthcare. So for most of you who don't want to know how long you have to live, others may still be watching and may know how long you have and may already be making plans for you. So let's make sure that we have the right goals, the right data, the right governance mechanism, and the right response process to ensure ethical development and implementation. Thank you.
And now for our next presenter, Dr. Brian Scheuchert, with his presentation, Following the Rabbit into Chemical Space.
Hi. Okay, bit of a change of pace. I'm going to talk about the explosion of chemical space and how it's affected drug discovery, something that's happened in the last 6 years. And to understand it, I think we have to go all the way back to Socrates, Plato, and Aristotle. Whatever their impact on Western philosophy, the therapeutic environment in which they lived was remarkably primitive. There were about 100 or so chemical agents embedded in the plants that they used to treat disease, and most of them were poisons that they would, use dose to have a therapeutic effect. Socrates famously committed suicide with hemlock. The active ingredient is the molecule shown right below the hemlock, conaine. Those of you who've watched The White Lotus recently are familiar with the suicide plant, cardiac glycosides, and those were the molecules, they didn't know they were molecules, that they used to treat disease. 500 years later, high point of the golden age of the Roman Empire, same sort of story. Dioscorides and Materia Medica cataloged about 600 plants that had therapeutic effect. Most of them, in fact, had no therapeutic effect. And the ones that did, there were, by now, opium was known, and a few others, but most of them were still poisons. And they would titrate to have like an anesthetic effect. But, it was kind of tricky because basically they're poisons and there weren't very many of them. So then the Dark Ages happened. Not much happened for 1,600 years. And then, middle of the 18th century, J.B. Priestley with nitrous oxide and the advent of the methylxanthines, caffeine, theophylline, theobromine, party drugs, basically. They had a huge effect on the West. The Jacobins, the Girondins, these were the Club de Jacobins and the Club de Girondins. These were coffee clubs. And they led to the French Revolution and much that followed, also the Opium Wars. The effect on treating disease was pretty limited, and still the number of molecules available to chemistry was pretty small, maybe by then 1,000. 1850s, huge expansion by the standards of the time in the chemistry available to humanity, the advent of German dye chemistry, and purified molecules all of a sudden. Modern chemistry emerges, and organic chemistry takes its name from the biosynthesis of urea, shown there at the far left. I didn't know this was happening. Anyways, but still, so now like maybe 10,000 purified molecules, now purified, not just plants, and not very effective in treating disease. But the basis in chemistry had been established, and setting the stage for this man, Paul Ehrlich, really the first person to think about disease in a modern way. Thinking about a target for a disease. Also with salvarsan, the first effective antibiotic, although admittedly very kind of poisonous too. But also aspirin emerges then. Some of the newer opioids like codeine emerge then. Some of the first muscarinic molecules. So we start to see actual chemistry translating in a meaningful way into therapeutics. That explodes, relatively speaking, with Alexander Fleming, Florian Chain, and the discovery and then the mass production of penicillin, and then following that cephalosporin, and then just the efflorescence of antibiotics as we know them, so the streptomycins, the tetracyclines, also the first antipsychotics. And by now, chemistry is in full flower, and maybe there's 1 million molecules with which science, the community has to deal with. This grows again over the next 50 years up to about 3 million molecules. And then there's a huge explosion, and it's that explosion that we're living in right now. And that starts about six years ago, where a new type of chemistry, really pioneered in Ukraine, comes to the field, and it gives us, like now, all of a sudden, 100 million molecules that we can access and play with. And 3 years later, that grows to 3 billion molecules. And 4 months ago, 2 trillion. And by mining this space with as advanced computational methods as we can, and reducing them to practice in experimental model systems, we and others have started to use these very novel chemistries from these trillion molecule spaces to treat circadian disease, analgesia, depression. We're treating mice, okay, for depression, but it's a start. COVID-19, a huge project here at UCSF that's been super effective, just been canceled, thank you very much. Inflammation, cystic fibrosis, psychedelics, homeostasis, calcium homeostasis, and pain. So it's, in that sense, the explosion of new chemistry has a huge impact on what we do and what the field does. The problem is the methods we've developed can search through and prioritize molecules for this target or that target at about the 10 billion molecule level. But the library, as of 4 months ago, is 2 trillion, and we expect next year it'll be 20 trillion, and the year after, who knows? And what we and others have shown is that as the libraries grow, we get better and better results. There's just more opportunity to find stuff, and we're stuck. So that's the great opportunity, and the great challenge is how to develop the new methods that can address that much larger space. Thank you very much.
Next, please welcome Dr. Katara Wilder with her presentation on precision immunomodulation.
Good afternoon. I am so excited to be here. I haven't even said anything. So I hope I live up to that clap. But I'm really excited to talk to you today about things that I get excited about, which is the immune response and the immune system. And one of the reasons that I'm excited about thinking about it and studying in our lab is because it's very effective at neutralizing pathogens that we get attacked on a daily basis by. And so it's been so good at its job that people have been thinking about, I should switch this slide. People have been thinking about ways that we can modulate the immune system so that we can treat various diseases, including cancer, which, as you know, is a very important topic. There's a number of people who get cancer. One of the problems with it, though, is that with immunotherapies that people have developed is that they only have about a 20 to 40% response rate. So only about 2 out of 5 people actually respond to these treatments, which, again, is pretty low. And so one of the problems with it is that even though patients initially will respond to the treatment, after initial response over time, they stop responding. And so I'm really interested in trying to understand what happens that allows that drop-off over time. How do the cells become desensitized? And one of the ways that I think it's important to study that is by understanding how cells think and process information, and how do they make decisions. And you may be thinking, I never thought about how cells make decisions. I didn't know that was possible. But it's something that is very similar to what we do on a daily basis. And one of the things that is a good representative of this is, how do we make decisions if there's a threat in our house? Some of the questions that you might be asking is there an intruder? What is the threat, and what is the threat level? And it's really important that you get this response right, because if you say that there is a mouse in your house, but you call the police, that's an ineffective response to the problem. You do not need to call for backup. Side story, there was one time where we had a squirrel that came down our chimney sweep. And again, in that sense, we did not need the police, but we did call the Terminator, and so that was very effective. And so something similar is happening with the cells in our body. They also have to make these decisions, so they go through a similar decision tree whenever there's a threat present. Is there an intruder? What is the threat, and what is the threat level? And if, again, similar to what we saw in this example, if the threat level does not need to have a recruitment of immune cells, we do not need that to happen. And so there's this balance that needs to happen, and I'm really interested in understanding how these cells make these decisions and what are the mechanisms that lead to this. And why this is important for immune therapies is if we can understand how these cells make decisions, we can control how they make those decisions using the various therapies so that we can use it to target cancer cells. And so one of the things that I think is important is, again, not understanding just how a single cell makes a decision, but how a population of cells make decisions collectively so that they can have a coordinated response within the tissue. And again, how can we then understand the mechanisms that allow that to happen so that we can then engineer cells to modulate or tune that response so that we can get an effective therapy response. So again, at the beginning, I said that only 20 to 40% of these patients have a response that lasts over time. And so if we can understand how do you keep that level up by modulating this response and keep it up at a threshold that you don't overactivate the immune response or underactivate, but you keep it at this level, that's kind of what we're interested in. And so we're developing a lot of various tools to study this. We're developing molecular tools so that we can understand what's happening. We also have projects where we're trying to engineer cells that can secrete different cytokines so that we can control their response. And I'm really excited about what we're going to do. But I hope that I get invited back in about 10 years so I can tell you where we end up, because I'm on the newer end of this journey. But thank you for your time.
Please welcome to the stage Dr. Sarah Knox with her presentation on restoring the salivary gland takes nerve.
Hello, everybody. I am Australian, and as you can hear from my accent, I apologise if you cannot understand me. I hope I'm okay. I'm also a long storyteller, but I'm going to nip this in the bud. So I have been studying salivary glands for a very long time, and I'm going to tell you this story about this major issue that people are facing. Now, I know that many of you know cancer survivors. Maybe you've had cancer yourself and you've got through that battle. There is a poor quality of life that comes out of this for many, many survivors, and head and neck cancer patients are one of these groups. So head and neck cancer patients, 100% of them are going to be treated, guess what, with radiation therapy. This causes a number of problems, doesn't it? And it's because even though we're trying to target the cancer, we end up with off-target effects, and so the other tissues are also affected. Now, the salivary glands is one of the big ticket items there that's affected. And so that's going to result in partial or complete destruction of those organs. Okay, so what does that lead to? Well, you know what it's going to lead to. It's going to be leading to a loss of saliva production. You're going to get xerostomia, dry mouth, and it's going to last you the rest of your life. It causes a lot of oral indications. Obviously, you will possibly lose your teeth over time, your gums. You'll actually have difficulty speaking, like I am right now. These are major issues for patients. This is reducing the quality of life, isn't it? And so they are desperate for treatment. What are they going to be treated with? And so we hear this a lot from clinicians. What does the clinician say to their patients? These are the solutions, okay? Water, milk, or saliva substitutes. Now, my uncle, he has radiation-induced damage to his salivary glands, and he uses milk. So he carries around a bottle of milk every day, and he says it's way better than water because milk sticks to your oral cavity nicely. It also so it lasts a bit longer. He doesn't mind the flavour, and it's way more comfortable than saliva substitutes for him. Okay, so I'm thinking, how can I help him and the millions of people who are affected by this? Because it's not just one time, it's ongoing for the rest of your life, as I said. Okay, so I've been studying salivary glands for, I don't know, almost 20 years. I know, crazy, right? So I'm going to tell you, I mean, all of you probably know the salivary gland like the back of your hand, but let's just go back and think about what this is. So this organ is composed of millions of these structures, okay? Millions of these structures, and these structures, acina cells, those are those pink cells up there, they're making the saliva, and that saliva is being taken out through this intricate ductal system into your oral cavity as you sit here. How is this preserved? Well, the preservation cell is the stem cell, and this stem cell is continuously making these acina cells so you can keep going for the rest of your life, and so this is really a form of repair. Okay, what's controlling these? Well, the primary controller, guess what? It's the peripheral nervous system. So here are peripheral nerves. This is actually throughout your body, as you know, and it's essentially controlling most of your organs. So the salivary gland, like those organs, is heavily innervated. Lots of nerves here, that's the green, wrapped around. And they're producing a myriad of factors, okay? And those factors are working on these cells. And these cells keep turning over because the nerves are there. And saliva keeps flowing. Okay, radiation therapy. What happens is an apocalyptic event. So what's going to happen to you is that you're going to lose most of these structures, and you're going to have this decimated structure at the end of the day. It is completely disrupted. You have stem cells that no longer do their job, right? They're no longer doing their job. You're not getting any repair. Your saliva production is obviously vastly depleted. And what's the repair going on? I said nothing. And guess what? This is deemed irreparable, unrescuable. It's never going to be coming back. That's the whole thought process right now. Of course, I then go, is it impossible? Can we not do something for these patients? And so we go back to healthy tissue. These nerves are important, as I said, making all these factors, and what we did was identify one of them that promotes those stem cells to make more cells, okay? Okay, let's just go and put that into this context of radiation-induced damage, all right? So what we did was we took one of these factors. It's a muscarinic agonist for those people who know that. And we get a synthetic version of it, right? And we place it in a gel. And the reason why I want to place it in the gel is because we're going to inject it into this tissue, and we want a lasting response. So the molecule comes out, and it's going to distribute out, and guess what it's going to do? It's going to act on those stem cells. I should tell you that there's no nerves here to make that. Okay, so I'm just reminding myself that there's no nerves here. Okay, so we did this in mice, of course. We haven't done it in you yet, but we thought, could it possibly be true? And guess what? It is true. You can return that decimated tissue to this regenerated tissue. Okay, so we are very excited about this, of course, and UCSF is too, thank goodness. So is NIH. Whew, phew. So Hydronova was created. We're a women-led company. Guess crazy, isn't it? And our goal is to get this back, right? This is a therapy that could run into other organ systems, because I just told you that nerves are everywhere. So they're controlling many different tissues. Can we do it? Can we use a strategy to go for other things besides this? But because of my uncle and the fact that I've studied salivary glands for 20 years, I am invested in this patient. So what we want to do is change their life, bring them back to the quality of life that they used to have before cancer, and wish us luck on getting that done. Thanks so much.
Please welcome to the stage Dr. Shubho Roy with his presentation, Engineering Stardust into Lifelines.
So good to see everybody. Welcome, and I hope you're having a good weekend start. So I'm Shubho Roy. I'm an engineer, not a life scientist by training, but I work with many of them and many of my clinical friends. So today, I'm going to talk to you about some of the projects we are doing here at UCSF. And let me start off with a simple number, 20. Seems very simple, but that's the number of people who are going to pass on today. They're not going to be with us anymore because of one simple problem that they can't overcome. They can't get access to a life-saving donor organ, and they die. And altogether in this country, we have over 105,000 people on the wait list. These are the sickest of the sick. And the vast majority of these patients are waiting for a kidney. And we only do about 25,000 transplants a year. Most of those patients have to rely on dialysis. And as some of you know, and if you don't, you will, through friends and family and through doctors, dialysis prolongs death, does not restore health. And clearly, this problem has become exacerbated because the mortality for dialysis patients is terrible, worse than most common cancers. Cancer is no longer the deadly killer it used to be even 5-10 years ago because of some of the breakthroughs you've heard about from UCSF. So here at UCSF, we said that's not an acceptable solution. We have to do something about this. So as an engineer, I take an approach to solve this problem by working with a material that's the most common mineral on Earth, silicon dioxide, material that has come to Earth originally from space. We are using silicon dioxide to create semiconductor silicon wafers, as you've heard the term Silicon Valley. And we're using semiconductor technology to create next generation of life-saving transplants. How do we do this? It turns out silicon is the most perfect man-made material ever. We can get it down to purity of 10 nines in the fractional setting. Think about that. We've built an infrastructure that gave rise to the industry in California for electronics. We here at UCSF are taking it a step beyond that. It's not about electronics. We want to take advantage of the electronics and build that in conjunction with cell therapy. And we're patenting the silicon to become a scaffold, biomimetic scaffold that can provide some of the essential functions of a kidney to start with. And what you see here is our first functional prototype of an implantable bioartificial kidney that's got silicon membranes and kidney cells that provide the metabolic function. And the silicon membranes not only provide a surface for the tissue to grow, but also provide an immunoprotective environment. And we've taken this work beyond just the lab bench. We've actually moved it into preclinical models. You're seeing the tests we've done in preclinical models where the device is implanted, does not require a battery, runs off blood pressure alone, and because you've created immunoprotective environment, we do not need immune suppression drugs. We do not need blood thinners. And what you're seeing here is an angiogram showing that blood is flowing through the device without clotting. This green shows the cells are alive despite no immune suppression. In this particular test case, we put human cadaver kidney cells into a pig and no need for anti-rejection drugs. And we're able to create urine. We are making an implantable artificial kidney that can replace a native kidney. Now, this is a prototype. Now we are thinking about the next step, and I welcome you to think about us at UCSF and what we're going to do. We are working towards the studies towards the first in human experiments. And to get there, we are going to scale up the device, go through the work that is needed to get through the FDA approvals, and then we can do the first in human studies, and that's what we call here at UCSF the Kidney Project. I welcome you to join us. Check us out on social media. Check us out on the website. But my friends, don't stop there. What here at UCSF, we've actually taken this a step further. This is a platform technology. We're putting cells inside an immunoprotective environment. By collaborating with colleagues across campus, in the School of Pharmacy, in the School of Medicine, in the School of Dentistry, in the School of Nursing, we've actually identified additional opportunities. And I'll highlight one of them first to the left, which is artificial pancreas for type 1 diabetes therapy. We're putting insulin-producing cells inside our device, stem cell-produced insulin that's coming out from the diabetes center. I'm working with the Department of Pediatrics and Department of Surgery to develop the next generation of lung support for patients that have had failing lungs, so they don't need to go on ventilators, or, more interestingly, for neonates whose lungs are underdeveloped, and this provides the next generation therapy till their lungs develop. So this is what we're doing at UCSF with silicon, and that's how we're converting stardust into a lifeline. Thank you very much.
Now, please welcome UCSF's next generation of emerging researchers from the Graduate Division's annual Grad Slam and Postdoc Slam to present their 3-minute winning presentations. Please welcome Dr. Reuben Hogan with his presentation, Protein Folding is Pretty Sweet.
When you think of something sugary, what do you see? Probably dessert from lunch. We're all familiar with the idea that sugar is necessary for energy. But what if I told you that sugars have other important roles inside the cell, beyond energy? In fact, sugars can be attached to proteins in a cellular process that's intentional. Why? Well, most of the time it's to help a protein fold so that it can reach its proper shape for its proper function. Your next question is probably how. I was actually on a run this morning down Market Street, past a business. Who here has been to IKEA, by a show of hands? When you purchase a table from IKEA, you want that table to look the exact same way it did in the store, right? And to ensure that, IKEA has factories that are responsible for producing table parts to consistent metrics every time. And they have checkpoints where they'll regularly assess the quality of those table parts. And you might even imagine that there's a QR code that reads all that information out. In this example, the QR code is our sugar. By reading the structure of the sugar, nearby proteins that are assisting in folding are able to understand whether to keep the attached protein or to scrap it. This process is so fundamental, it's used on almost every cell of our bodies and on over half of the proteins encoded by our genes. In fact, we think this process underlies diseases that we see today. For example, many of you may be familiar with Alzheimer's disease, a condition that affects 1 in 9 individuals over the age of 65. It has long been known that this is a disease characterized by 2 misfolded proteins, amyloid beta plaques and tau tangles. And yet, despite that knowledge, there are no widely accepted diagnostic tests, and our treatment options are modest at best. So, what do we do? By using a special instrument called a mass spectrometer, we're able to read those sugary QR codes to try and understand if the attached protein is folding well or not. In this way, we can monitor cells to then say, what events trigger misfolding? To go back to our factory analogy, it's as though we can see what part of the assembly line may be failing and potentially even understand how to fix it. Getting this right could mean a large step forward in a disease that has already robbed so many people of their memories, their personalities, and their lives. Thank you.
And with our final presentation today, Dr. Sonia Nocera with the power of the sugar mama.
I have to confess, I like mammals, all of them, no discrimination here. I even think humans are cute, especially when they're born. But wait, don't judge me, let me explain. Newborn mammals require just two things to grow strong and healthy: breast milk and sleep. That's it. Breast milk contains all the nutrients to fuel the entire development. How is this even possible? He makes me feel women. We got some power here. I am a neuroscientist, and I study the production of myelin in mice brain. Now, myelin, like the coating of a wire, insulating neuron. Myelinating neurons speed up brain signal up to 100 times, make the brain super efficient. Think of it like the difference between going work, try to take the super reliable San Francisco public transportation, or zoom in there in a Formula 1 race car. Boom. In particular, for my study, I focus my research on a tiny sugar contained in the breast milk. It's not any sugar. I like to call it the hero of the brain because it affects the production of myelin in the brain. Now, look at this slide. We have two mice brain slices. One comes from a normal mouse, and the other comes from a transgenic mouse. This means that it's transgenically modified to not absorb this magical sugar. Do you notice any difference? It seems that the transgenic mouse have been on a diet. Less white, less myelin. So, how a tiny sugar can affect so much the entire brain development? It's like to say how a pinch of salt can transform a bland soup into a gourmet dish. Mwah. I want to understand the mechanism underlying this process. I analyze mice brain to figure out what is the mechanism behind and how we can modify it, how we can control it. This is crucial, not just for optimize the formula milk, but also for helping people with myelin-related disease, like multiple sclerosis, for example, where myelin is destroyed, and how we can repair, how we can help. Well, often repairing is just the recapitulation of what's happened during development. If we can crack the code, we might be able to produce new treatment to boost myelin production. So, what is the take-home message from all of this? Well, everyone deserves a sugar mama, literally.
Are you proud to be part of UCSF? I'm going to ask all the speakers to come back on stage. I did not prompt them for this. I'm going to ask all the speakers to come back on stage. I didn't prompt them for this, so we're going to say it one more time. I'm going to ask all the speakers to come back on stage. Thank you. Ladies and gentlemen, please give them a round of applause. All right, we're going to do a quick test because you're going to go downstairs and you're going to talk to them. So today we learned about, first one, aging well. Second one, AI and ethics, thank you. Then we learned about, oh, look at this. Number 4, very good. Whoa, we're out of order here, but that's all right. We'll go with.
We're testing you.
That's all right. Sugar mama, I love it. Next. Excellent. Next one. And finally, the historian. Awesome. All right, you have an opportunity. Well done, well done. There's nothing quite like hanging with a bunch of smart people, including our students. And you know, because this was you a few years ago, right? Thank you, everyone, for joining us. These wonderful folks will be downstairs to chat with you. You should have a lot of questions. Please feel free to bombard them. Thanks, everyone.